So today is a very, very happy day for me because this is the last video of the Simplified revision series. Simplified revision series for GATE biomedical exam. Where the idea is typically if you're in the last 2 months or so, okay, of the GATE biomedical paper preparation, suffices to look at this one series of videos, okay, where all topics, all subjects are covered. Okay, so far we have covered, in fact, every other subject except analog and digital electronics, and we'll do that today. Okay, because the series comes to an end, so that is very satisfactory for me. Okay, one thing is whether I have the fortune to have you as a student or not, right? I managed to bring material, study material available to anyone, right? Publicly available to anyone, thanks to YouTube again. And anyone can use. And ideally, actually, uh, you just stick to this one series. You can technically get a single digit rank. Okay. So that much information, you know, and preparation aid, suggestion tips, all of that there in this one series. Okay. Because it comes to conclusion today, I kind of feel satisfied that you know anyone can prepare, right, without me actively intervening. So that's very, very good. And we'll finish this off. And so today we are looking at analog and digital electronics. And so for each subject we are looking at 4 years of PVQs starting from 2020 to 2023. Quite bare minimal concepts, and the PVQs are kind of sequenced in a increasing in an order of increasing difficulty. So we start from easy questions, then how details are added on top of each other, how the questions are made complicated. We try to add look at PVQs in increasing layers of complexities. We solve them. We discuss related issues and all that. Okay, so my impression about ADE, this is, unless you already know the subject in and out. Okay, this is one subject that if you're preparing for the GATE biomedical exam, you should. It's really, really efficient to skip this. Okay, at least information than what is there in this video. If you decide to spend time, at least if you know this 2 hours, 2.5 hours very well, okay, that makes sense. So typically every year I have about 20 questions from 4 years. Okay, so this is 4 years, roughly 20 questions. That's approximately 5 questions per year. Questions, right? Out of these 5 questions, irrespective of the branch that you are in, okay, about 2 questions are hard questions, approximately, or hard. Hard as in super hard. Then, you know, if you're an expert, if you like analog and digital electronics as a student, as a subject, you might still find it hard to answer some of these questions. Okay. Or, in other words, there is also a lot of too much recall. Okay. The time spent to recall, memorize, formulas and info here, concepts here is quite a lot. Okay, and your preparation gets highly, highly inefficient if you are to focus on this. Even IN students, electronic students, and this year electrical students used to have a difficulty answering about roughly 2 marks. Even those who are doing very well in the electronics paper, they are finding it hard to do uh, attack these 2 questions. Having said that, three questions roughly every year. That is not easy, but that is moderate. So there aren't any easy questions. Even the three questions somewhat moderate, and there you need to know reasonable analog and digital electronics to answer those questions. Okay. If you know the basics, that is what we discussed in this video, can answer, about at least two questions here. Two of the moderate questions you can answer just based on information that is contained in this one video. Okay. So typical suggestion is to skip the subject. Just in case you decide to learn this or you already know this, make sure you at least know information in this one video. Okay. And yeah, to make it really efficient, I'm also not going to discuss solutions for hard questions, solution theory concept for hard questions, or like where it's like totally out of the blue. Not going to discuss, but we'll focus on this. Okay. So that our discussion is somewhat streamlined and efficient, and it's worth all of our time. Okay. And if I have to actually categorize the questions that you need to know, let's also do that. For some miscellaneous questions like that, almost every year there is a question from ZDC, TAC, okay, business. There are miscellaneous, and the NIQuest, request, um, SNR, SNR, SQNR, SNR, ADC, DAC, and then CMMR, CMRR. That in this case, notice they had this SQNR. There are typically questions from this. Okay. So the intersection of electronics and signals and systems, measurements and all that. Then diodes, important topic. In ideal, diodes are fairly easy to answer. Okay. And ideal, that is A, in the forward, it's forward bias, it's open. Forward bias, it's shorted. Reverse bias, it's open. It won't let any current flow, right? It can flow along the direction of the arrow, right? So that model works. Linear model, even you can skip that. Then there is an exponential model for diode, because exponentials take ln on both sides. Exponential equations become linear equations. This is also fairly easy to answer. Okay, so exponential model for diode. The question that I was reading is based on exponential model, first order system, or it's an exponential model. And then op amps. Typically, there is a question, and DAC basics. There is a question. Electronics, digital electronics, where you have things like the Boolean algebra, and from my experience, the logic is, this is what I would consider as the basics. Okay, and on top of this, if combinatorial circuits, that's a plus. Sequential circuits, if you also know the basics of that, okay, that is fine. But notice, again, op amps, I am only referring to basic things. The real problem is there are questions from BJT MOSFET, and you have to recall a lot of relations. Okay, it gets highly inefficient unless you are, you need it for your day to day life. Okay, you are working in that electronics engineer, working on designing circuits day in and day out. Okay, recalling, there isn't a need for recalling so many relations. Okay, from a gate exam perspective, and sometimes they also start asking questions from, you know some of the miscellaneous things. Say Schmidt trigger is given here. Somewhat of a non-linear circuit, right? So there are often questions on this where you can easily make mistakes. So there are lots and lots of difficult questions also. Okay, that I'm going to write here. Okay, there is DJT, but and literally, you know, hot questions, not miscellaneous questions, literally hot questions. So some of this, of course, it would be really smart to skip this. Okay, these are the typical topics, and today, in fact, we'll spend significant amount of time with op-amps. You'll also spend some time with digital electronics. Okay, the basics. Electrons, it's electronics, right? Okay, having said that, notice the next question that we have here is a diode model. Is an exponential diode model. I also found one more diode question, but that's somewhat recall based. If you can recognize the circuit, you can answer it just like that. If you don't recognize the circuit, this is it's not answerable in the gate time frame. Okay, so one question is it possible to share a specific topic for PAM? Okay, so this is again, op-amps, fortunately, almost every year there is at least one question. So we have about 5 to 8 questions in this PYQ discussion, which I'm going to discuss all of that. Okay. So ideal, you should know how to deal with ideal op-amps. Okay. And many op-amps are, you should be ideal. Most of you can answer that. I'll also teach you today. But if you somehow recognized in electrical circuit, say this impedance is very, very useful, right? You can look at the frequency response and all that. If you're familiar with impedance of circuits, if you are familiar with Z, dealing with complex variables, complex numbers, then any question based on filters also is answerable. It might look complicated, but still answerable. I'll show you a couple of examples. Okay. And there is also a trend where ideal op amp in the linear range, right? They are targeting because I showed you there is a Schmidt trigger and all that is there in the syllabus, right? For that reason, they are targeting they are targeting this nonlinear saturated op-amps comes under saturation or saturated or positive feedback op-amps. This is a sort of if you know ideal sufficiently, that would be very good. Okay. But because there is almost every year there is a question from the I will discuss some simple, you know, places where the ideal doesn't apply and where there is a positive feedback and how to analyze PVQs. Fortunately, there I have many different types of PVQs, so it's kind of fairly we can compare and contrast where ideal will apply, where ideal won't apply, and all that. So we'll also do that. So this is a list on all that. Okay, in a filter, a integrator, differentiator, inverting, non-inverting, summer. You can put all a club, all of that together. An ideal op amp kind of has all of that. If you know how to deal with it, essentially you know how to deal with all of this. And I used to expect questions from, a differentiator and all that, the, common mode rejection ratios and all that. But so far, I haven't seen any, at least know how to deal with ideal op amp. So this is a breakup. Okay. where typical questions are. And of course, we'll also learn the basics and we'll solve those. Okay, with a quick intro, let's start with with the first question. Yeah, because we did signals and systems, the measurements and all that. Now, there are always questions from ADC. Okay. Yes. Okay, so there is voltage in. You have a analog to digital converter, and the digital has 10 bits, I suppose. Okay, and then you retain six most significant bits, and then you throw away four least significant bits, and then you again do a digital to analog conversion. Okay, so take the sinusoidal curve, you digitize it and try to reconstruct. Okay, get back the analog form. That's your V out. Goodness. Yeah, it's a 10-bit Nyquist ADC. Four LSBs are dropped, six are retained. Okay, that is six important decimals or digits are retained. Okay, process, of course, you're going to lose some information or you're going to increase your noise, right? Decision noise. Based on this, the peak SQNR at the DEAC. What is the peak signal to noise ratio at the output? So this is a question that where you have to recall a relation. This is actually a deep result in signals and systems. Okay, uh, this goes back to Bernard. Suppose this goes back to Bennett. Bernard Shaw is there in literature, I suppose. So Bennett is there in uh, communication. So it goes back to Bennett, and the speak SQNR happens to be. Does anyone know the relation here? There's a SQNR. When you digitize it, the signal to noise ratio is given by 6 Avogadro number is what I remember, right? Times the number of quantization digits plus 1.7, 1.7. And the whole thing is in decibels. Yeah, approximately this. Okay. The way that I remember, yeah, 6.02 or the Avogadro number 6 plus there is this point 7. Can someone quickly suggest a mnemonic for this? 17, 1.7, 6 and 7, right? In fact, Avogadro number and let's say 2 bits, okay. Worst case scenario, you don't remember this 1.7. Let's say this is 6.06Q2. Okay. Let's see. So now at the end of the day, you're doing a 6-bit quantization. Notice I just kind of like digitized it, right? Throw over the decimals and all that. So 6Q plus 2, your Q is 6. Q happens to be 6. Your ending resulting digitization is qubits. So that makes the 6Q plus 2, 36 plus 2, you are over here. So even if you don't remember the 1.7, I think 2 bits, right? That is fairly easy to remember. 6Q or 6N plus 2. Or precisely 6.02Q plus 1.7. So here you have to recall this and the answer here is let's make it 38, 37.8. Yeah, also some of you have the answer keys ready so that we can quickly also cross check or verify. Okay, let's move on to the next one. Forward bias, the current of a silicon diode is being calculated from the exponential model and the VA characteristics. And diode current ID at a voltage drop. This is fairly easy, okay? And because it's exponential, I'm going to show this. Look at voltage versus current relationship in a diode. Got it reasonably straight. This voltage across it, there's a current here. Okay. Let's also look at a diode. Really, if current you can kind of like can flow this way, ideal diode, current cannot flow this way, right? Current cannot flow against the arrow. That is something that most of you know. And notice ideally they make it like this. Voltage is across the diode is negative, current is zero. And then depending on the circuit that it's put in, okay, it can take whatever value you want. There can be any current, and that depends on what the circuit that diode is put in. And that external circuit is drawn here as a dotted line. This is what most of you know this, right? You have the forward mode, you have the forward bias, and you have the reverse bias. And sometimes this is the ideal model, simplest model. You make a there is a change in voltage across the diode. So this you slightly write it this way. There is a threshold, you know, voltage here, right? You kind of approximate it this way in the forward bias. This is a threshold voltage. Or even across a voltage drop in a real diode, the potential drop is non-zero. Okay, even in forward bias. So that you kind of this is roughly 0.71 and all that, depend on the diode, silicon, germanium, whatever it is. So this is shaking, this is shaking. More realistic model for a diode is this one, where is an exponential scale, where you approximate this using an exponential. And that relation, the current as a function of voltage, current, if I write it as a function of voltage, is an exponential, it's a growing exponential. Okay. And this relation, notice this explodes with h e power a normalized thing. So they normalized with a thermal voltage. And two things. So this curve is passing through the origin. So you have a minus one. When V is zero, current is zero. And when V is like a V is tending to minus infinity, okay, current is tending to the saturation current, IS. This value is non-zero. It's too small, okay, uh, but it's kind of non-zero. Okay, so you have an IS over there. It's an exponential relation. In the side, it is saturated at a small negative current. It is passing through zero. It kind of explodes exponentially. So that is the relation that we have here. I also added one term at a time so that this is reasonably, you can easily comprehend it. You can write it down if you kind of remember it that way. And here, what is given as a diode current ID is 2 points of interest. Let's use at 0.7. You have your current is 1 milliamp. Hey, what would be the current at zero point 0.8 milliamps. Okay. So at zero point 0.7, info is given. What do you need at zero point 0.8? So because the exponential relation, you can take ln on both sides. It's a straight line. Given 1 point, you can, given 2 points, or, given 4, you can find the, uh, it's a straight line fit. You can easily fit a straight line. So the questions are based on that, right? You could also say for this calculation purposes, you can do the calculation with this, or here, what is the closest to, right? You can also slightly approximate this as is e power minus v by vt. Can forget that minus 1 in this case. Not necessarily that you'll get the answer steps earlier if you have this approximation. What is given is 1 into 10 power minus 3 current at, let's say, even approximately at is e power, the voltage is 0.7. Uh, Vt, this is in millivolts. Let's make it units the same. So how many volts is this into 10 power minus 3? 0.0253 volts, right? So 0.7 by 0.20253 volts. You want this? Hey, what is the current I? This I approximately at e power 0.8 by Vt, that is 0.0253. This is a 0. This is a 0. You can divide these two and quickly is will get cancelled. You can find what is I. You know all of these constants, right? You know this voltage, you know the constant Vt, you know this constant, you know this constant. The I will get cancelled. If you divide this equation by this equation, you can find the only unknown over here by taking ln on both sides. Because things are in the power, you can undo the power by taking ln. Okay, ln ln. Can someone take the ln and tell me what voltage you are getting here? So, in fact, if I have to do one step, your current is approximately 1 into 10 power. So, in milliamps, so okay, 1 into 10 power minus 3 e power zero point 0.8 minus 0.7 by the voltage 0. I'm dividing one equation by the other. Here you can take ln on. Hey, you don't even have to take ln, right? We're not trying to find any unknown constant or something. Yeah, just do this calculation. So you want the answer in milli. So for that reason, I'm going to hit the current in milli so that I get back the answer in milli. Can just do this calculation. 0.8 minus 0.7. About 52.68, something like that. 52.068 can have answer this. I wanted to do it approximately, even even otherwise you can retain that minus one, still get the answer. Okay. This is fairly, you can get the approximate, the answers differ by a lot, right? By orders of magnitude. 0.1, where is 2, where is 52, where is 90. It's easier to spot it. So I did that approximation here. Otherwise, you can get the answer. Okay. So three models of diode and exponential relation, because you can easily do, even if you say something like the thermal voltage is an unknown, given 2 points, you can find the unknown by taking ln on both sides, right? Those kinds of problems are possible. Okay. Now, the next question that I have here is, there is one more diode question where you need, it's not basic diodes. Okay, you need some ability to recall, or at least you should technically recall the diode circuit, diode application. So I'm not going to discuss that right now. We're heading to op amps. Okay. So for the given input voltage, there's an input voltage given here. Uh, Functional circuit shown below. The output signal will be here. You know, there are two rules of op amps. Let's make life simple. Okay. Let's look at how to analyze an ideal op amp. Two rules for the gate exam. First rule, learn how to deal with the ideal op amp. Second rule, look at first rule, right? That is, learn how to deal with ideal op amps. The two rules, if you look at an op amp, three terminal device, okay? There's an in there is a non-inverting terminal, there is a plus sign, there is an inverting terminal, minus sign. There is a non-inverting terminal, there is an inverting terminal, there is an output terminal. The two rules that you need are, so the voltage in the two terminal, let's call this B plus and B minus. There is a V out here. Number one, op amp will act in such a way that the two input voltages are the same. Sometimes this is referred to as a virtual short. It behaves as if these two are connected by a wire. That's a property of the op amp. Okay. And second rule, let's call this the current through the input terminal, the current through this input terminal, non-inverting terminal, inverting terminal. So the second rule, you have currents are equal, not just that, equal to zero. That is, no current can enter an op amp, ideal op amp. The input resistance is like really, really high to do that. Almost infinite. So no current can enter the op amp. Always remember the way this is an active thing, this is you can amplify voltages and all that. The reason you're able to do that is, of course, this can draw power in from an external battery. It's taking in, it is taking in power. Sometimes this is connected to a, let's say, plus 10 volts, 15 volts, whatever it is. This is sometimes connected to minus 10. It is taking in power. This is an active device. So passively, it cannot increase the gain. Input voltage is one, it cannot make it two, right? But it does it by taking external power. So energy and all that is still conserved. Okay. That is one thing. And these two numbers are also not so important in case of an ideal op amp. For circuit, okay, in fact, if you look at this circuit, say this is at plus 10, is at minus 10. If you look at the how this thing behaves, the output voltage here, if you had to plot that, okay, you're going to get a line like this. It's saturated at plus 10, this is saturated at minus 10, minus 10, 10, and in this side you have plus greater than V minus, that is, it is, the inverting terminal dominates. In the side you have minus and then V plus. With the voltage that you have it at the two terminals, which terminal dominates, based on that you get this response. And sometimes this is idealized as a like this. That's an idealization. It's either this or that. Okay. And you can use this as a comparator. Hey, they given the two inputs, which one is higher, which one is lower, right? V plus is higher, you get positive 10 as output. V minus is higher, you get negative 10 as output. You can do that. But the most important thing over here is this. If you know this, okay, this is in fact this is a bare minimal thing you need to know that box over there. The two inputs voltages needs to be the same. There cannot be any current inside, into the input terminals. Quickly look at an example circuit. There is a minus here, there is a plus here. The negative feedback loop. Okay, let's kind of ground this. So I'm looking at what is referred to as an inverting amplifier because I'm supplying the voltage to the negative terminal. And before I supply that, let's give a resistance, input resistance. Or in fact, let's make it give a resistance here. Let's give an input here. Objective is to look at what the output is. There is a resistance here, call it RO, output feedback loop resistance. Or many times this is your first resistor and this is your second resistor. You could also say this is your input resistance, okay, and this is your output feedback loop resistance. Let's stick to R1 and R2. Okay, fairly easy. In fact, let's stick to this RA and RO. Let's look at the two rules. Notice if this is grounded, so this is at 0, this input at 0, reference is 0, let's say, that makes this voltage anywhere here as 0. Where I apply, the voltage in the two terminals are the same. V plus equals V minus. The virtual short. And if there is any current, of that should flow here. None of it can enter this. So if you write current conversation at that particular node here, shows in should all exit through this feedback loop. Okay. So current there is 0. So whatever shows here, should all of that should exit through here. None of it should enter here. That current has to be 0. Now we can quickly write down this current conservation equation. You have current here as Vi minus 0 by Ri equals 0 minus V naught by R naught. This current equals that current. This is your second. Let's quickly simplify this. This simplifies to E naught by V. Can someone simplify this and tell me what this is? The 0, this is 0. Take this R naught over here. E naught by VA is negative naught Ri or R2 by R1. And this is what we refer to as my Wacom tablet is slightly aligned that way. I'm trying to correct for it, but still I end up, there's a minor calibration issue. Okay. No, this is overcompensated. It's a wonder I'm getting at least a parallelogram, a quadrilateral. This is what we refer to as an inverting amplifier because the sign kind of becomes negative, right? So let me write it. This is inverting amplifier that comes from the voltage is supplied to this negative inverting input. So inverting amplifier. If it's a non-inverting amplifier, again one line you can write it down. The two rules you can write it down, you can get it. Some of you can recall it. Okay. Very good. But let's look at here inverting amplifier. So notice technically your R naught can be greater than Ri. That means your output voltage can be greater than Vi. So it can amplify voltage, right? The gain can be greater than 1. Is it possible? Isn't energy consumption any issues with that? Because it's drawing in power. So it can do that, right? There is an external power source involved here. Because of that, the gain can be greater than 1. If not for the power, there is no power source, the amplifier cannot do it. It's a dead thing. Okay. So that's where the two lines sticking out of it, like a mustache or like this cockroach antenna, right? That's where that comes into play. And one more thing, because what I did here feels good if we have impedances here instead of resistances. So for this setup, V naught by Vi as minus Z naught by Zi. There is a resistance capacitor, inductor. Even if there is an inductor, you can technically analyze that also. The same thing. The current here is voltage by change in delta V by impedance equals delta V by impedance. You get the same relation. So even you have capacitors, inductors, what we did still holds good, still applies. Okay. With that, issues with recording. Yeah. With that, let's look at this problem. Okay. Uh, for the given input voltage, the IN is 10 to the functional circuit shown below. The output signal will be. There are two parts to this. So the functional unit has two subparts. As far as I can see, there is a subpart 1. So having known this, rest of the things is divide and conquer. Can you kind of spawn this pattern in the thing, right? And then there is this one more subpart over here. Can we label this subpart number one, subpart number two? And any of you label this? Give it an English name. We already looked at subpart number one. And it also kind of helps to simplify this, let's say this bias resistances. Like it's not there, okay. Kind of makes your life slightly easy. What is part number one? I just discussed it. It has like input terminals. One of them is grounded, input is applied to the one, you get an output. Who is this VM? Yeah, the input voltage is, oh, Madhu Olala. Okay. Input voltage, in fact, is applied to the non-inverting terminal. So what it goes to is, saturates to kind of like old school. So one is the comparator, and your two is a differentiator. If you kind of recall at least that much, you can answer at this stage. Input signal is sine. It's applied to the positive terminal. Okay. This is a sine. Let's look at two cycles. Okay. Let's put some landmarks here. So let's look at the output end of the first subunit, that is a comparator. It compares things. Input higher than 0 or lower than 0. Wherever it is higher than 0, it saturates to plus 12. Wherever it's lower than 0, it saturates to minus 12. Does it happen instantaneously? Let the ideal world, it does happen. Okay. Goes like this. Second one is a differentiator. Means it's going to throw out the derivative of this. And notice this is through the non-inverting terminal. So there will be negative sign. There's no change in slope here. There is no change in slope here. There is a sudden spike here. There is a sudden spike here. It has a reversed, it's through the inverting terminal. The spike will be in the other direction. So the spike will be in the reverse direction. Okay. This direction. And that corresponds to the output here corresponds to this. There is a negative spike. There is a positive spike. In between, there is no slope change. The output, this option, I don't know whether it's A, B, C, D, and all that. That figure corresponds to that. That option corresponds to actual output in this circuit. Notice this option corresponds to the output at the blue dot in between, be between. Comparator, you get this. Had it been a differentiator, okay? Yeah, notice, is it an inverting? No, there is no inverting with the gain one and all that. There is no inverting amplifier involved. So this is totally out of the circuit is not given there. Even if it were an integrator, can notice if you integrate this blue curve, what you will be getting is integrator again through the negative input terminal, it becomes thus, and it can technically, it should get back here. Okay. So perhaps this option is not really an integrator. Okay. Something looks like an integrator. Um, okay, that is okay. What makes an integrator and a differentiator? We will answer quickly. Okay, this is really even this option is not an integrator. Okay, but it's going supposed to this area nullify that nullifies that area. So technically, it should get back to zero, but it's going to plus 12. So yeah, this is you're not going to get this fairly easily. At least this bit, you're integrating, you would get. Integrating this blue, you'll get that. Integrating blue. Okay, the answer is this stage. Some of you might wonder, hey, what is this differentiator integrator business? Okay, quickly answer that also. So this, I suppose, most of you remember, right? What we have here is an yeah, now there is a mnemonic. If the capacitor is at the input, okay, it's a differentiator. The capacitor is at the feedback loop, it's an integrator. Okay, let's quickly see that. Hey, this is so whether it's inverting terminal, non-inverting terminal is based on how it is drawn there. Okay, this is input is going to the inverting terminal. It's a non-inverting amplifier that I have drawn. So now if you look at V naught here, and if you look at V out, sorry, this is supposed to be V out. If you look at VI, let's call as R out and RI here. What we have seen is VI by VI equals minus R naught by RI. Okay. Let's hold the same setup. In fact, let me just call this not and ZI. Okay. I already said that. Don't repeat that. There is Z naught here, there is ZI here. In two cases. For E naught is a capacitor. Z naught is capacitor. So your Z naught is 1 by J omega C, 1 by SC. ZI is, in that case, your E naught by VI happens to be, okay, minus 1 by RC. Notice V naught is 1 by SRC. RC is time constant, VI. If I slightly write it this way, you can recognize that form better. Yes, this is just the Laplace transform of the integral of input. This is what we refer to as an integrator. As I think Madhu Olala pointed out. So if this is your capacitor, the resistor there, what you get is an integrator. You can also talk about this in terms of frequency response. Is a low pass filter, high pass filter. Again, if you use impedances, you will get it. Okay. Yeah, you can also look at the frequency response of this. But right now, no, just the integrator, differentiator. If you look at, if we have it the other way around, a differentiator, in this one thing, I suppose Madhuvalala is trying to read my mind. Sir, if you do this, you will get a this filter, high pass filter, low pass filter, and all that. Yeah. If there is a differentiator, you do it the other way around. Okay. Capacitor goes to the input, and then this goes to the output. So notice comparatively, if I write it this way, you can easily compare. Your Z, you put a resistor in the feedback loop. Input, you have a capacitor. What you get in this case is your V naught by Vi plus this is R by 1 by SC, that is SRC. In fact, there are some initial conditions, Laplace transform, out of that. Let's keep the initial conditions slightly out of this, okay? The current discussion. And then, this is just SRC. This, S times SRC, of course, if you pull this um, VA to that side, V naught is just, and I have to give it some, slightly readable form. There is a time constant, SVI. This you recognize as a derivative of the input voltage, SC. This is derivative, differentiator. Of course, the moment I'm using impedances, I'm doing that in the frequency domain, Laplace domain. Okay. So do that in the Fourier domain. Yeah, there is a negative sign also. It's inverting. There is negative sign here. There is negative. The derivative. So which is why, even if you don't remember that, whatever I told you, right? But technically, you can now see. Okay, there is a bit of nuisance going on here, of the timing. This is inverting amplifier capacitor at the input, non-inverting terminal feedback group. There is a resistor. This is a differentiator, and you get the spike response. There, at least you can certainly, answer with better certainty. Let's move. Notice. So now they can throw out capacitors, capacitors. This thing, a piezoelectric sometimes often behaves like a, capacitor. So they can throw anything here. You can easily analyze this. Do this push. This is grounded. This is at, let's say, this is at 0. Actually, shorted. This is also at 0. And whatever current flows here, be the current flows here. Okay. Here, notice QS CV, Q equals CV. Then, our current I equals rate of change of charge. Your capacitor is a function of X. This is a displacement sensor. Huh? Yeah, parallel plate capacitor. Then displacement changes with time. The input voltage, on the other hand, kind of like it's activating this capacitor. Okay, this is, let's say, constant. Okay, what you get there, first important point, Di is a constant there. Okay? C is a function of time. So that makes it I dc by dt. We are used to this, right? C dvi by dt, where the voltage, input voltage changes. Here, the input voltage is fixed. input voltage is a constant. The capacitor changes. So when you differentiate that, what you get is VI dc by dt. What you get is VI dc by dt. Okay. That should be equal to the current in the sum. That is 0 minus V naught by R. Already virtually shorted it. Voltages are same. I applied it. Current here is current here. So capacitor expression is given. X is a function of time. This compositional derivative, f of g, derivative of f function of t, right? And get the answer. Your V naught minus or di dc by dt. So derivative of that, that I suppose is minus epsilon a and all that is constant by x square. Okay, into dx by dt. Dx by dt is just k, right? So at this stage, you kind of know the answer. So you're so this implies continue that. Okay, that equals Okay, there is a you know I put a split there. That equals it's minus cancels. We have r pi epsilon a. I'm going to write this as x into x. Dx by dt is k. This term is nothing but the capacitance. So we have r di c k by x. Get option. Negative sign. Where is the negative sign question? Is this? I already made that correction, right? 5 minutes back. Yeah. So let me again, for completion's sake, let me recall this. So here we have this is inverting I O. We know that VI by VO or VO by VI is minus RO by RI, where this is here RO, this is here RI. And the voltage is supplied to this terminal. The other terminal is inverting terminal is grounded. Now we should also look at this case. The inverting amplifier. The inverting add minimal. We should also know non-inverting. Differential amplifier and all that. If any of you remember that, it's a bonus. Okay. And again, if I show it side by side, it's easier to compare and contrast. So which is I typically like this is familiar now. This is can be associated with what is familiar. So I like to show it this way. Let's make a plus there. and minus. Same circuit, but I'm giving the input and output differently. It's grounded. Cannot put a feedback loop. If I put a feedback loop here, it's positive feedback loop. Okay. Daily, the system don't be stable, so you cannot do this. So what you have to do is, let's again draw it that way. But you supply the voltage here. This bit is grounded, and then you end up with a negative feedback loop. You have VO. Again, let's write this down. Notice if this is VA, this has to be virtual short. This is VA. The current here happens to be the current there, right? Current here happens to be the current there. So 0 minus VA. Again, let's call it R2, R1, or R0, RI. I prefer calling it as R0 and RI. 0 minus VA by RI equals current there, that is VA minus V naught by R naught. Now, can we simplify this? Let's bring that VA same sign. Can you tell me what is V naught by VA in this case? The gain in this case. In won't be 1. This is going to be 1 plus, hey, just one line solid, okay, plus R naught by R. Negative sign here. This is a non-inverting amplifier. So just in case they give the voltage, to the non-inverting terminal, we also got that. So this is non-inverting amplifier. So with this, now you kind of equipped to actually answer some op-amp questions that they give in the gate exam. Let's look at some questions. So we already saw two, right? Question, they throw the circuit at you just to threaten you, okay? Notice they again see, just like engineering mathematics, you have to be brave enough to look at this circuit, okay? So have here is there is an inverting amplifier here. There is an inverting amplifier there. There is a non-inverting amplifier. They are cascaded. This is fairly easy. So if you look at it that way, if you can isolate it, how do we know that there is a this is going to negative? Voltage is applied to negative terminal. Voltage is applied to negative terminal. Voltage is applied to positive terminal. And you recognize that it's a very, very easy. This is a circus line. You can tame it, or it is already tamed. We just need to deal with it, right? It's not a. This is not a wild lion to be threatened. It's a lion, but it's a tamed lion, circus lion. So this is one thing. Let's look at. Yeah, this circuit. Circuit is actually somewhat more involved, I suppose. So suddenly they thought, hey, you guys know how to time, a circus lion. We will give a circus dinosaur. That sort of question is this, right? Um, Look at it. There is an inverting, yeah, this is inverting amplifier. Current through this input will be added. So This point acts like a summer, the summation of current date. This point, there is a summation of current date. So there is a summer, winter, summer, autumn, Vivaldi's summer, right? There is a summation going on there. And then there are two things coming, they are getting added up. What is the individual thing? A capacitor in the loop. Is it a differentiator or integrator? This, I suppose, in an integrator. This is an integrator bit. And this is a, so this bit is integrator. Okay. And this chunk over here, this is inverting voltage is applied there. There's an inverting amplifier there. Okay, things are being summed, but what kind of an amplifier is this? That again is an inverting amplifier. This bit is also inverting amplifier. Three inverting amplifiers. There is an integrator. There are two summations going on. Tamed velociraptor. Slightly harder to deal with. Still, like the circus lion, that's the circus velociraptor. Okay. They're velociraptors in real life. No, but they're on gate exam. We have this, so we have to deal with this. Look at this inverting amplifier first of all. Oh. Let it be that too. Let's go back. Let's look at this inverting amplifier. First, I need to know the input here. Input that is coming to the, or yeah, the inverting amplifier. I don't know what that is. Yeah, actually, that is zero because this is grounded. But I need to know the input here. What is the input to the inverting amplifier? I need to know that. Quickly notice this is grounded, virtually shorted. This is zero. This is going to zero. This is going to zero. There is R here. There is 2R and 2R in parallel. 2R and 2R in parallel. Effectively, there is a resistance of R. So there is voltage division occurring between R and R. So the voltage here, V out by 2. Voltage gets divided between R and R. Let's also draw this so that your R is visible. So I did this. At, yeah. So the input, this is the input to this inverting amplifier. What is the output here? That is fairly easy to say. Output will be the input here. The gain is R by 2R. So the gain is half with a negative sign. So here it will be minus V naught by 4. It's an inverting amplifier. This is also an inverting amplifier, but with a gain of 1 and it changes sign. But it changes sign. What you get out here is V naught by 4. This is V in, so this is V in virtually shorted. Now I think you can write down one equation. If there is no current through that to this input terminal, you can write summation of current here and then you can relate the input to the output. That equation is current through the 4R should exit through this 4R and this R. Oh, V naught minus VIN. In fact, current through the 4R is V naught. Let's also make it VO and VI. Okay, V naught by 4. That's the current minus VI. This is a change in voltage across 4R by 4R. should be equal to the current exiting that red dot. So that equals Vi by R, the other current, Vi minus Vo by 4R, because there is no current through the input terminal. Specifically, this non-inverting terminal, there is no current there. So I'm writing current conversion on this junction. And conservation of KCL, right? Current conservation, charge conservation. This is Kirchhoff current law, KCL. Can we simplify this and tell me what this V out by V N is RRR? We cancel this, yes, SMB, SS, on that, SS. Can I simplify this? We got V naught 4 minus Vi equals 4Vi Vi minus naught. AVA 6Vi 6Vi equals naught by 4 plus V naught. 5 by 4 V naught. V naught by Va and 6 into 4 by 5. 24 by 5. 5 by 5 is 5. 20 by 5 is 4. So this is closer to 5. Can you tell me what is that? 24 by 5. Yeah, 24 by 5 is 4.8. This option. So notice, essentially wrote down one line. Know how to, if you can recognize the subparts, if you're familiar with that, this is answer is one line. But this is a problem where I have to look at the subparts and solve it. But if I am writing a current here, the voltage division current, no current through this input terminal, you don't recognize this is a inverting amplifier. It's going to, you cannot solve the, you are going to waste time when they get exam. Which is why at least this much you need to know. Let's do one more example of this. Filter is designed using op amps, resistors, capacitors. So they also throw in capacitor. So what we know, we can deal with C, impedance, in the plus domain. Amps are ideal with infinite gain, infinite bandwidth. V naught of S by Vi of S is an all-pass transfer function. The value of resistor R2 is. So I already told you there is an inverting amplifier here. There is an inverting amplifier here. There are two summations going on here. There is an integrator there. Integrator. Okay. Then let's kind of follow the dots. If this is V naught, this is V naught, really easy. I'm following this line along. So this is the input to the inverting amplifier. I'm following that line. V naught. That makes this out. So these two are getting a minus V naught. 4 by 4 minus V naught, I suppose. So Vi minus V naught, that is getting integrated through the inverting terminal. So what I get here is the summation of the two signals. Okay? Let me write that down here. Let's call this V center. Center happens to be the input A minus V naught. This is the summation of the two signals VA plus minus V naught. So that is VA minus V naught. And it's an inverting amplifier. So there is a negative there. The ratio of impedances is Z naught is 1 by SC. This is R. So that is 1 by SCR. This bit is a summer. I cannot color code it any further. Okay. Let's do the same thing again here. This is VI. In fact, let's make this V naught in blue. Okay, in case you're trying to. This is your VI. Then notice this. This is an input here. So what shows up here is fairly easy. This inverting amplifier. The gain is 1. 2 by 2K by 2K. That is 1. So this is minus VI. There is one more summation here. So the two things are added. Gain of 2. This again is inverting with a gain of 2. 10 by 5, that is 2. Okay. Let's make BC in the rows so that so notice your B comes out is a summation of these two signals as minus VA. Whereas one second. I slightly make this. Yeah, let me just write down the current equation at that point. Okay. It's an inverting amplifier. It's summish. Things are being summed, but trying to make it compact. Yeah, let's just do this. So V naught is minus 10 by 5. If you're wondering, I mean, let's put this by 5. Okay. You have a 10 there and you have a 5 there. This is the gain comes. One is the gains are also different. So I have to make a slight correction. V naught will be VI as a gain of 10 by R2. VI into 10 by R2. And there is a summer there. You take VC to be 10 by 5. BC, that will be 10 by 5. And if she should also have a change in sign. So I'm going to make this minus. Combination of two terms, but one of them has a negative thing. So minus VA become plus VI, and then VC becomes minus VC. Or so good. Any questions here? Instead of one equation, you got two equations. So if any of you wondering about, hey, what is the summation, you can think of superposition. Hey, just have this voltage, what will happen? Have this voltage, what will happen? Yeah, because you are applying a VA there with a gain of 10 by R2. You are applying a VI to a non-inverting amplifier with a gain of 10 by R2. Now let's simplify this, okay? So you have V naught equals 10 by R2 into VI minus of V 10 by pi. So that is minus 2 into VC. There is also minus there. So that becomes the 1 by SER into VI minus V naught. If you rewrite this, okay, just take this V naught inputs to one side, outputs to one side. You can leave the inputs there as such. This is the input part. The output part will be, you already have a V naught. Okay, let's take it out. That had a coefficient of 1. And then this plus 2 SRC comes to, minus 2 SRC comes to the side. And there you go. And if you slightly tidy up this equation, I can take the VA common and you got this. And all of that I just got from, yeah, I substituted, I substituted VC here and in the second equation. I got that. These two combined together. So V naught by VA is this term by this term. At this stage, we can answer this is an all pass transfer function. The location of poles and zero. This is a first order system. Okay, first order pole, first order zero. This has a root, this has a root. One of them will be in the numerator, one of them will be in the denominator. Location of zero equal to location of pole. Zero wants to pole. The roots of these two terms inside the bracket has to be the same. That means 10 by R2 needs to be equal to 1. Roots of those two, that is the solution of that equals, so S equals, set a, find the value S by setting the term inside the bracket equal to 0. That will be the pole because that will go to the denominator. This is in the numerator. Set this to 0. Okay. This is also, it's not 21. This is 2. Your R2 has to be 1. Oh, sorry. R2 has to be 10. And I am getting that because the roots of the numerator has to be same as the roots of the denominator. It has the same roots. It has to be the same equation. That makes 10 by R2 has to be 1. I am comparing this term and this term there. Okay, you're not getting this part. So, but at least till are you all fine till this equation? So at this stage, notice I am answering on my R2 is 10. Okay, I'll tidy up this, rewrite this equation so that it's slightly more efficient. Yeah, why the 10 by R2? So I'm going to rewrite this equation. Okay, so which term I have to erase and no, let's see if there is some space. There is a bit of space here. Yeah, here is. These are only in the Laplace domain. P naught of S, A V I of S equals by R2 plus 2 by S C R. Okay, by that's a numerator, and then denominator I have 1 plus 2 by S C R. All pass transfer function, the body plot should be a straight line. It cannot go down or it cannot go up. If there is a unbalanced root or pole, it will go down or go up. Wherever there is a root pole, it's going to change the directions. Unless the root and the pole are at the same location, it will change direction. Okay. So on this stage, I want the modulus of this to be 1. It's a all pass filter. Bode plot doesn't change direction. It's a straight line. It's a constant. So that can happen, let's say, when, you know, the net gain is 1. You can say it that way. But a slightly better way of stating that is location of the root and the pole has to be the same. Okay. So notice solution of this is what we refer to as the zero. Solution of this is what we refer to as the pole. It has to be at the same place so that it's all pass. Okay. Because it's an APF, location of pole and zero should be at the same place. Okay. Why that is the case? Hey, wherever there are roots and poles, the body plot will change the direction. So there will be a non-zero gain, right? No change in direction. They are at the same point, their effects will cancel each other. Or even you just do this all pass. So let's say the magnitude is 1, okay. No frequency, there is no frequency preference. All frequencies are one and the same. All S values are one and the same. In that case, when will that happen? The denominator and the numerator amplitudes are same. Let's say when 10 by R2 is 1. You can say it that way. Slightly better way is location of poles and zeros are 1. Okay. And notice the solution zeros, let me explicitly write it. Got the zeros there. Solution of that, I got the pole here. Solutions of this. My zero O equals, okay, 1 second, totally out of this. Zero equals minus 10 by R2. Okay. Actually, minus by CR 2, 2 by 10. That's my zero. That's the solution of the numerator. Pole is equals plus 2 by CR. So for is this clear? Yeah. Now, because it's an all pass and this first order pole, first order zero, all pass filter, the zero location should be the same as the pole location. That means this term has to be one. Yeah. Zero equal poles. Yeah, and that means auto equals. And that is what I was telling you here. Now, hey, so notice this is actually fairly. I told you this is a tamed velociraptor. Of you might be wondering what is a zero, what is a pole. So that's why I had this biomedical filters, biomedical signal processing playlist, right? I have been saying this for a long time. Short 5-minute videos, 20 videos or something like that. I'll start from basic complex numbers, amplitude, phase, and all that. I will go till all pass filter. In fact, I actually go a little beyond this. Okay. If you have seen it, this will make more sense. It's also publicly available, right? But even otherwise, I try to put it in a language that you can at least follow this discussion. Okay. If you are hoping that someone would simplify this further, okay, no, you're fortunate to have a friend, something like that, roommate or friend, they might consider, okay. And that might also depend on how far away you're from the examination. But I am sure, first of all, no one is going to answer you this. And I think hardly anyone, first of all, hardly anyone can answer this outside of the IITs and, things like that. That if you want someone to further simplify this, like, but any roommates and all that, they're very good. You should try your luck. Okay, so that brings us even this question is done. And so far, notice there's a question that even IN electrical engineering students might find it hard. In fact, this is one of those hot questions. And I kind of answered because op amps is once you know the two worlds, once you're kind of familiar with it, if you approach it, it's not that hard. Maximum one equation, maximum two equations, right? That's why I did it. It's doable. Okay. But is it error prone? Can you kind of get lost? Yeah, that is possible. So be careful. Okay. Now, now comes this question: the positive feedback loop. Ideal op amp with an infinite gain. Ideal op amp. Okay, infinite. Hey, what happens to a non-ideal op amp? Okay, let's not really complicate it. Whatever I discussed till now, if you know that, that's fine. So notice the loop is going to the positive thing. There's a positive feedback loop, which can grow uncontrollably if there isn't a counteracting negative feedback loop. No, you don't know. There are both feedback, positive feedback as well as negative feedback. Do you know which dominates? Okay, if the negative feedback is strong enough, it dominates, then the system can still be stable. You don't know what the case is. Okay. There is also one more question. There is a positive feedback loop. There is a feedback to the output is taken and given back to the input. Positive feedback. You have to deal with the systems carefully. Okay. And so, what is the difference? So, let's show that again. The positive feedback loop. There is a positive feedback loop. Feedback loop to the non inverting terminal. Notice there are always feedback loops to the inverting terminal, negative terminal, negative terminal. That's where the loop was going to. The loops were kind of going there. So now the things are slightly different. What do you do? Which one dominates? Presume things are normal, solve for it. Okay. So in that, this is where there's a linear range. Your output is saturation value. This is, this is not a normal op-amp. Linear range is in between the saturation. So the output is either 10 or minus 10, for example. You're not in the linear range. These rules don't apply. Solve the problem. If you are getting a value between 10 minus 10, you are in the linear range. That's your answer. Either getting 10 or minus 10 or sometimes higher, you're not in the linear range. Your answer is saturation voltage. Okay. Again, I'll show you two quick examples. Fortunately, we have two PVQs. So the first year they gave this, there is a positive feedback loop. Whenever there is a positive feedback loop, output will be saturated. So this will be minus 10, right? That's what students wrote. Then say 2021. That's what students wrote. There is a positive feedback loop. Output will be saturated at the negative terminal value. So answer will be minus 10. They wrote it, okay, this year. And next year, there is again a positive feedback loop. Output will be saturated at which one is higher? The 1 volt, I suppose, is higher. It will be saturated at this terminal. So again, they wrote it as minus 10. They got it incorrect, okay? So solve this. Okay, assume linear. Check if your assumption holds good. If linear, so it starts with a big, 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 big if. See what happens. What's your output? If linear, if in linear range. Don't know that. If happens, what should be the output? You're checking the output in the linear range. In linear range, let's, everything holds good in this case. If so, let's write down the current laws and all that. Let's say there is one unknown, let's call it B. This is sh- virtually shorter. Okay. So I got 0.1 minus V by 1K. Okay. That equals V minus V naught 2K. KK will get cancelled. One equation where I got it from the top. That's also right. No current through the non-inverting terminal. That's where I got that equation. One more equation. There is no current through the there is no current through the non-inverting terminal. I had to write that. There is no current through the inverting terminal. I got this equation. So let's look at this non-inverting terminal, the plus terminal. No current through that. That gives me 1 minus V 1K equals V minus V naught by 5K. Solve for V and V naught. So this equation says this is 0.2 equals 3V minus V naught. Equation says 5 equals 6V minus V naught. Can you solve these two equations and tell me what is V naught? Your V equals equations two unknowns you can solve for it. Multiply first equation by 2. So that is 5 minus 0.4, 4.6 equals 3V. V equals 4.6 by 3. I got it from this equation. I got it from this equation. Now I'm taking those two equations and solve it. And you just solve me and tell the roots. V equals 1.6. 1.53 I'm getting, but okay, 1.6. Why am I getting 1.53? And your V naught equals 6 V minus 5, 4.36. Why am I getting, can, the equations are all correct, right? They're just 5 minus 0, oh, 5 minus 0.2. I did 5 minus 0.4. 0.8 divided by 3. Yeah, 1.6, and then your V naught is 4.6. Your V naught within linear range. Is this linear? Let me draw that figure again. The top, this is at 10. At the bottom, this is at minus 10. In between this, there is a linear range. The question is it linear? Really, it's a vertical line. In reality, it's like a slant line. Okay, this is this way. Whereas this is somewhere over here. This is still in the linear range. Okay, it hasn't touched either the 10 volt or minus 10 volt. Here, I know, yes, this is in the linear range. Okay, so even though there is positive feedback loop, the negative feedback is dominating. How do we know that? By solving. I know things are linear, and then your output is 0.6. Because was it an if in linear range 4.6, it is in linear range. Okay. So presume linearity, what happens? Yeah, linearity is correct. And it's a comparator in between. So the slope is 1. The slope is 1. So 4.6 to 4.6. Uh, I know, okay, even forget that. Okay. Okay, now let's get a contrasting scenario. Same thing I'm going to do. Okay. So this is if linear, what happens? Rules holds good. Linear, we got two equations. One is, let's call it here. Really, these two are vertically grounded. And these two voltages, virtually short. So that is V. You have the current and the current through the non-inverting terminal. That gives you 0 minus V by 2R equals V minus V out by R. Simplify this RR get cancelled, so that equation as minus V equals 2V minus 2V naught. This is 3V minus 2V naught equals 0. There's one equation. And then if you write it at the bottom, to know current through this inverting terminal, you got 10 minus V by R equals E minus BO by 2R. RR cancels. And then what you have is T minus 2V equals V minus V naught. So, in other words, V minus V naught equals 20. Now, can you solve and tell me? So, so from this equation, I got this. From this equation, I got this. Can you take these two equations and solve and tell me what is E and V naught? We are more concerned about what is V naught. We add the two equations. We subtract the two equations. V naught is 10. And then V is also 10. Subtracting these two, I got V naught is 20. Both V and V naught. I'm getting V naught as 20 and V T by 3. So at this stage, I know it is 20. The saturating voltages are plus 10 and minus 10. It cannot be above plus 10, it cannot be below minus 10. It is at minus 20. This is non-linear. Rules don't apply. So, this is if linear, right? No, doesn't make sense. Presume linear, it says, hey, things are non-linear. In this case, the positive feedback dominates. Okay? Whichever terminal has a higher voltage, that it will go to that saturating voltage. So inverting terminal is given a plus 10, non-inverting is given 0. So this term, this input will dominate. Input here will dominate. It will saturate at minus 10. Because this is 0, right? It almost behaves like a comparator. What is here is certainly higher voltage. Okay, this will dominate and then goes to minus 10. This dominates. First of all, it's positive feedback dominates. And in the positive feedback, compare the two inputs. Hey, this voltage is higher, so it goes to negative saturation. Okay, because it's linear, I make that conclusion. So the answer here is minus 10. Had we got an answer less than between minus 10 and 10, that's still in the linear range, and we can go write it out. But 20 is obviously beyond the saturating voltages, right? To make the distinction clear, maximum voltage is 10, minimum voltage is minus 10. What we solved for was in between those two, 4.6. Makes sense. Can be linear. Solve for it. Maximum is plus 10, minimum is minus 10. When we solve for it, we are getting 20. Hey, how can that be? No. Okay. So that I think we are also done with op amps. What is left with? Hey, there is one more thing. With trigger, switches, and all that. Notice there is a positive feedback loop. A reference is grounded. We inverting terminal is grounded. The ground can be at any voltage. We set the reference to be zero, but voltage can be anything, right? Accordingly, this can behave. Notice because of this, the output voltage is at saturation. There is no counteracting negative feedback loop. So here, this is certainly saturated, and based on based on what the input is, it can be either saturate to the V plus or V minus. Okay, this is a bistable, behaves like a switch. This is also bistable. It can either saturate at these two, either of these two voltages, V plus and V minus. So it's bistable. The output is at saturation. Notice there is no counteracting negative feedback loop here. So there is no question of linearity, non-linearity. There's only a positive feedback loop. That's how we are not doing any linearity, non-linearity calculation here. It just saturates. Okay, now there are a few more digital electronics questions. We'll answer that and we can stop this. Okay. So op amps, almost every 2 years there are two questions. Okay. See, sorry, every year there are at least two questions. Digital electronics. One is in expressions. Yeah, Boolean algebra. If you're lucky, you get a question on this. The bare minimal things that you need to know for that kind of summarized here. There is an AND operator or operator. Symbolically, at least, it helps to know. And A, right? This is A. In fact, let's look at the OR operator. This or that, A or A, just A. A or A bar. One of them, if one is zero, another one is positive. So either one of them will be positive or one of them will be one. So your output is one. A or plus one, you got a plus one here. This, right? A or zero, your output is going to be A. Some of you might be wondering what the OR operator is. So at least OR and AND, I'll put it okay. Two inputs, X and two inputs can be 0, 0, 0, and 1. And then you have at least the OR and AND, right? The OR, X or Y. Most of you know this. Either one is positive, you get a 1 there, right? 1, 1. Either one is positive, it's 1. In this case, neither 0, and that's the only case you get a 0. And X and Y, right? This is OR. And you have your AND. Even both are positive, the output is positive. So this rest of the cases, this is 0. Okay. So that makes it notice. If you go back here, A or 0, right? In fact, A or 1, this is fairly easy. Only one determines the value. So the output is 1. A or A bar, one of them has to be 1. So this is output is 1. A or A doesn't matter, just the value of A. A or 0. 0 doesn't matter, only what A is matters. Similarly, you can write A and A and A bar. One of them is 0, output is 0, the AND operator. A and 1 depends on what the input is, A. A and 0, irrespective of what A is, output is 0 because one of them is 0. And what I have here is this AND option. No, this is fairly easy. You can do A plus B, complement of that. right? That is not of NAND operator. This will be A bar, B bar. Okay. This is NOR operator, A or B, not of that. Okay. This is complement. Let's write it. A bar sometimes written as A dash, right? Sometimes written as A complement. This is a complement of it. Okay, let's stick to A bar as complement. A is 0, this is 1. If A is 1, this is 0. And then you got A or B complement of that, and then A and B complement of that. Okay, you can, these two are equivalent. How do we quickly check it? Yeah, you know what this, you know how complements work. You know what is OR, what is NAND. So given this, complement or a NOT gate. Okay. Okay. Given that, you can find what is NOR and NAND matter. So these two are fairly easy. The important one here is this adsorption. Again, you can prove this, but I'm going to take this for granted. Okay. A or A complement B. There is redundancy there. Okay. Quick way is redundancy. When both A and A bar, they show up along with B. No. Suffices for one of them to show up. Which one? A. It's either A or B. Okay. This goes by the name adsorption. And this is very, very important. Adsorption. And there is a corollary for that. A bar plus AB. Again, A bar and A are redundant. Only one of them. Okay. Is a corollary. A bar or B. No, this much at least, most of the Boolean you can answer. Okay. I also presume for most of you, what I just said is, I just recall, right? So let's go look at this question. Let's take this X bar, Y bar, A. Take common things and simplify, right? So there is bar, Y bar, sorry, X bar, Z bar is complement. I mean, common there, right? So let's pull it out. Things are commutative, and you can also typically presume associative. Okay. But let's say things commute. So this is Y or Y bar. Is this Y or Y bar? This or that? Respective of what Y is, one of them has to be one. Yeah, this is one. So I'm going to technically just cancel that. X bar, YZ. This I can also pull out an X bar. So this that became one. And I can pull out the X bar. Got Z bar plus YZ. How much is this? A Z bar and Z. There is a redundancy. What did I say? This term doesn't have to show up. It's just Z bar plus Y. And again, things commute. I just showed that B goes together. So it's either between this or this. Can we do one more thing? Let's do yes, okay. Just let's do yes and then we'll wind up, okay. If I answer yes, we can answer. So let's do this. Again, common things. This is notice X bar Z is common. XZ is common. X bar Z bar plus 1. XZ bar plus 1. Again, this is a 1. The 1. Then you got pull out the Z and then this X bar plus X. Right. This is a one. So that makes it C. Yamma. OPL is the answers. You can quickly verify other things. Okay. It's fairly easy, doable, 2 marks. This is a question that you don't have to skip. You can always say it. But sometimes, some of you have struggled with normal algebra, right? Confuse yourself with Boolean algebra. This is slightly different. And unless you are not reading this as A is A square, right? Um, yeah, this is so unless the whatever short table that I have given, uh, unless this is confusing, okay? This questions like this are answerable. If this is confusing, just skip it, okay? Because again, I have seen students who have difficulty with normal algebra, right? So with them, sir, what is going on with this addition? What is going on with the subtraction? Things like that. So don't confuse yourself in that case. Okay, now we have this XOR operator. Let's also look at XOR. XOR, okay. So quickly, let me give you four options: A, B, E, D. You name these gates. Tell me the names for symbolic representation. S- Op, label A, label B, label C, label D. Just want to make sure you know what these are. Symbolically, what gate is this? Not used to this. You have an AND, an OR, Then you have a XOR, and this is a NAND. You have a NOT. Familiar? If you're not familiar, at least right now, a symbol for AND is this. There are two inputs, there is an output. There is an X, Y. There is an output here. There is an X, Y, and or X or NAND. If you did not know this, I just introduced that to you. Okay. So let's put X, Y. 0, 0, 0, 1, 1, 0, 1, 1. You have X plus Y. Have sorry, this is and Y. Have X or Y. And then NAND does just take that NAND XY. You put a complement to that. Or flip this table. X and Y, when both of them, sorry, when both of them are 1, there's a 1. Rest of the cases, there's 0. Fairly easy. So this is 1 in this case. The outputs are, one of the outputs is 0. This is 0. One output is 1, this is 1. Take XY, you will be not of this, right? So this case, this is complement of that. XOR, when the outputs are different, it's 1. When the outputs are same, it's a 0. Let me repeat that again. Outputs are different. X is 0, this is 1. X is 1, this is 0. Again, let me make a minor correction. When the inputs are different, output is 1, right? X and Y are different, output is 1. X and Y are different, output is 1. When the inputs are same, output is 0. So what an XOR is, and the way to write it is, it's either this or that. So this is X, Y bar, or X bar Y. Just one of them has to be, non-zero. This is X bar Y plus X Y bar plus X bar Y. This is your NOR gate. And what is the in simple English, outputs are different. This is out positive, right? Just remember that bit. So with that, we can answer a few more questions, right? QRS or Boolean variables, XOR operator. So this is this plus, is what I wrote here, not as if. Or Y. You can either write complements that way or you can write complements this way. To be consistent with what we have been writing so far, it's this. That's the XOR operator. Okay. And let me tabulate the results again. You have X, you have you have Y input and your output X. So your X or you have say 0, 0, 0, 1, 0, 1, 1. When the two things are different, it's a 1. Two are different, these two are different. It's a 1 in that case. Two are same, it's a 0 in that case. So this is if inputs are different. Okay, now you could, quickly simplest trick is verify is that things are associative. Typically, when there is a only when there is a, you can presume that you can quickly verify this. So are things associative? Answer is you could say this is recall, or you could also substitute values and verify. How do you substitute values and verify? Let's look at easy one. Hey, when QRS is one, this is one, this is one. Inputs are different. So the output here has to be a zero. This has to be a zero. This put together. And that X on one, the outputs are different. The input is sorry, the inputs are different, the output is one. So this is correct. I just verified it. So also, verification here apparently is easy, I suppose. If any two of the Boolean variables QRS or zero and the third variable is one. So it can be any way. Let's just use, let's say this is zero, any two, but that's fine. Let's say I'm just trying to verify Q is zero or is zero, yes is one. Two or zero, other one is one. In that case, what happens to this? Let's just verify, okay? This is one, zero or zero, that is a zero. Two things put together, the zero. Two are different. So you are expecting a one day, a zero. So this option is not correct. You are expecting a one day because the inputs are different. This is not a correct option. Any correct option should also hold good for the other cases, right? That's so this is for any QRS. Take QRS to be 111. Okay. So let's say this is one, this is one. That makes this. I just presume that this to be one, this to be this is one, and this is one. This is zero. This is zero, zero. Thing put together, two and zero. That is a zero. We have to compare zero or zero. It cannot be one. There, I just assumed all of them to be one. It doesn't make sense. A, I just verified for this case. Special case, Q equals R equals S equals 1. Special case, it did not hold good. Okay. And be careful with verification. We cannot prove, we can only verify. So I found a counter example, so I know it's incorrect. Okay. Just because you're choosing QRS randomly for that random selection, it happens to be correct. Doesn't mean that expression is correct. If you found a counter example, you can move on. Okay. That is, if found the expression is incorrect, it's incorrect. To say it's correct, you have to check for one or two more values. Typically, you hit the counter example fairly easily. Okay. And to make life simple, the selection that I make, some cases given here, just try that. Don't try any new case also. Is it associative? It happens to be associative. We can verify that for the gate. Okay, if you put it this way, things are different, it's different, right? So you could verify it, but let's say from recall, uh, no issues here with associativity. I'm just picking them. Okay. This happens to be in yes. I didn't really verify that. I kind of recalled that. Have time at the end of the examination. You can quickly check randomly again, at least for these values. Does it hold good? Okay. This is one and one, this is zero. Zero or one. That is one. This is one and one. Say QRS is one. You can quickly verify. Say for the other case, quickly verify. It will hold. But given three inputs, you have 2 power 3. You have 8 possibilities. Notice, given two inputs, you have 2 power 4. Sorry, 2 power 2. Two possibilities. Three inputs, QRS. You have 8 possibilities to verify. So it's time then consuming. Be careful. Okay. To do binary addition, you should be able to do two things. Digits, and then you should be able to do carry. Right? 1 plus 1 is how much? 10. So it has summation as 0 and then there is a carry of 1. Right? You can split it into two parts. What is given is the summation part. Okay? That is known as. This is the addition is summation and carry. If you can do those two operations, you can do this, right? Carry addition is summation and carry. Handling summation and carry operations. If you can do sum, if you can do carry, you can do binary operations. This actually corresponds. So what is given here is this sum part, because you are trying to do summation of two bits. For a correct implementation of the sum, how do you do this? Right? This is also fairly easy, but just that you should be able to track these lines. Hey, and one more thing, there is a triangle with a dot. That is our not operator. That dot, sometimes, you put a triangle, arrow with a dot. Okay, that's a not operator. Let me highlight that knots over here. There is a knot, a knot. Yeah, there are two knots. Be careful about it. For the sum, this is fairly easy. Input, output, sum. Again, possible input outputs are this. Possible input outputs. What should be the output here? These are the four possible inputs. Summation of 0 and 0 is 0. Summation of 0 and 1 is 1. Summation of 1 and 0 is 1. What is the summation of 1 and 1? Summation of 1 and 1 is 0 is 0 carry of 1. You have to deal with the carry separately. This is why you're only looking at the sum part. So this is how summation of two digits work. And notice this actually corresponds to XOR. Inputs are different, it's a 1. The inputs are same, it's a 0. So the sum actually corresponds to XOR. That equals y dash xy bar plus y bar x. Either, this or that. This also I kind of introduced it today when I introduced XOR. So I'm not going to elaborate that further. Now our task is to there's an and, there's an and, there's an and, there is an or here. So you're adding things. This is a summation or, right? This is fairly easy to deal with. This is and 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 right? And there is an or. So things are added up. That input is added to this input is added to this input is added. So if you look at the and what comes here, this is where you have to be careful. I have x, y, and then I'm taking complement of x and fitting it here. Okay. What I am sending here, there are three, and can have three inputs. This is x bar, and this is y bar. What shows up here, d1 x bar y bar. Do we need that term? d1 x bar bar. Do we need the term for XOR operation? Need x y bar and x bar y. Do we need x bar y bar? Our summation, what we need is this, two terms. Do we need this term? Don't need that term. We can say that by setting d equals 0. If you set that to 0, this term is fine. Okay. Again, in simple language, the combinatorial circuit. We learn that after learning logic gates and all that. But I'm trying to, like, with basic gates, this is what you do, right? You don't need the term. You can negate the term by setting this data to be 0. That is, I don't want it. I don't need that. Neither. So T1 is 0. T1 is 0. So the answer at this stage is either this option or this option. This option is ruled out. This option is ruled out. One more thing can answer. Which one is different? Let's do for D2. Okay. 2. Your notice the input got here. 2. Right? It helps to have some bit of space here. So I'm going to write this slightly here. This is the easiest of the terms. D2 happens to be, output here happens to be D2. It is coming, Y is coming without modifications. Do we need that term? Again, we don't need this XY term. We can set it to happily not needed. We can set D2 to 0. Not needed. At this stage, we can answer. At this stage, your D2 has to be 0. Has to be 0. Makes option A correct. D0 corresponds to x bar y. Okay. What is left here is x bar y, and then D3 corresponds to x y bar. We need both those terms. So D0 and D3 cannot be 0. We cannot set that to 0. You can go verify that it's needed. For example, you need this input, you also need this input. That input happens to be x bar y D3. So D3 you cannot set it to 0. You have to set D3 to 1. You need x bar y. We need x y bar. You are getting y bar and x. So D0 also you cannot set as. We also double check this. I think this last problem, 4:30, right? We'll kind of stop. 5 minutes or something like that. Circuit shown below. Y is a 2-bit output of the combinatorial logic. You have 4 inputs, A0, A1, B0, B1. What is the maximum value of Y for any given digital inputs? Be careful. Notice A0, A1, B0, B1. You got totally, 2 here, 2 here, 2 possibilities here, 2 possibilities here. 2 power 4 possibilities, 16 possible inputs. You don't have time to check all those possible inputs. Okay. One quick way is you can backtrack. If, hey, is this feasible? Can I can I get can I get one? Can you backtrack and verify? I'll quickly show that. Okay. So this is not this is time consuming. What I'm going to do is backtrack. 10 possible inputs, time consuming. Which one gives you the maximum value, right? So we will rather do backtrack. It takes 27 days or lilies in the, lilies to cover half of the pond. How many days will it take for it to cover entire pond? 28 days. If you backtrack, that's very easy. If you try to forward track, this is very hard, right? Again, in chess and all that, sometimes, hey, what is the ending that I'm trying to get? From that, you can backtrack and play. Gets easier, right? You have to do the same thing. You have to backtrack. What do you mean by that? Is this possible? Is a one here and a one here possible? And quickly recall T is like when both is one, this is fine. This is XOR, right? Let's also write that. You have and and is and or or so. If this is a one and this is a one, notice I'm backtracking. If Y1 is one, this has to be a one and this has to be a one. Okay. This has to be a one and this has to be a one. This cannot be a one. Both the inputs here are one and one. This cannot be a one. So this option is ruled out. Just ruled out. This is not possible. I cannot get that as the output here. There is contradiction. Even initially itself, one step down the line, there is a contradiction. That's not possible. Let's try something else. Is this possible? Is one and zero possible? If this has to be a one, it has to be one in this input, it has to be one in this input. One and one, zero is possible. Has to be one here. Okay. This has to be one in this input, and it has to be one in this input. And this has to be one in this input. So it's a D, both the inputs should be one. Then only I get one as the output. But XOR, this input is 1, this input is 1. I cannot give it 1 as an output. There is a contradiction. So again, this cannot be 1. I ruled that one out. There is a contradiction slightly deep inside. Okay. Let's try. And I am also trying things from the descending order, right? Because I want the maxima. Oh, is 1 the maxima? No. Is 10 the maxima? Is 0 the maxima? That's where I am right now. Is the maxima. This is a 0 here. So the inputs can be different. Let's make this 1. Then this has to be a 0. It can be either, this is 1, that is 0. Two inputs are different, you get a 1. This is possible. What happens here? To get a 1 here, you have to get a 1 here. And you can get a 0 there. Because this and a 0, the output here is 1. Both inputs has to be 1. This output is 0. If one of them is 1, the other one has to be 0. And on top of that, the NOR gate also works. The inputs are different, 0 and 1. The output is 1. Makes sense. Can I get a 0 and a 1 here? Yes, that is possible. So no, I'm slightly writing that 1 over there. Can I get a 0 here or a 1 here? Yes. For example, I can quickly give you, right? There are many, many ways. There's a OR gate, there's a OR gate. Can I get a 0? That's the input. Can I get a 1 here? That's the input. I can get a 1 here for this case. I can also do this. I can also do 0, 1. Maximum I can get. It's possible to it. 0, 1 is feasible. 0 and 1, 1 are rejected. So this happens to the maximum. Because those two are rejected out of the feasibility set. They cannot be the solution for the maximum value. 0, 1 is the maximum. 0, 0, of course, is smaller. So I'm not even bothering to check about it. Backtrack and answer those. Hmm. Once again, if you go down, from here on, hard problems, okay? Yes. Anything to do with time and all that, right? Logic gates with time or sequential slightly can be tricky. This specifically is very hard. Okay. This is a question that I would consider skipping in the actual examination. Okay. BJT offset, there are too many things to record. Okay. So notice there is a diode circuit. This happens to be a doubler. If you want to quickly design a mosquito bat where you take the battery voltage and kind of amplify it by a factor of 10, 100 and all that, you need to use some sort of a doubler, right? There's a voltage doubler here. Why that is? So you will be using a circuit similar to this. Okay. Why it's a doubler? That's very hard to do, explain. Okay. This is a doubler. So whatever voltage doubler circuit that is there in your mosquito bat, and if 2.5 is applied, you get output of 5. If you can recall this a doubler, you can answer. There are many, many, many diode applications. And this comes with familiarity and recall. If you don't know that, just feel free to skip it. PJT MOSFET are really hard. There is too many things to record. For that reason, I would rather use my memory recalling, actively recalling few other things in medical imaging and bioinstrumentation. Question shows up, I would skip that. But if a model for a BJT is given, in this case, this is the electrical circuit question. This is actually a model for BJT. But with the electrical circuits knowledge, you can solve this. Okay. For that reason, I would answer this question. This is a model for BJT. Example, electrical circuits is fairly easy, right? So in comes here. It gets split between 5 and 5 kilo ohm and 1 kilo ohm. I can write this IB to be a fraction of IN. What fraction? Current division, right? So total is 5 plus 6 in the denominator, and then more current through this 1 ohm resistor. So 5 by 6 into I. So this is a dependent circuit. So this is IN. So this is 100 times IB. So I know this value right now, and that should get split between this and this. How does so this current 100 IB should get split between this and this. So I load, I can quickly write down I load is a fraction of 100 IB, and there is a negative sign. Okay. Because this current gets split this way. What fraction? That fraction happens to be 10 and 1. Okay. And more current through 1. And IB also, so that is minus 10 by 11 to 100. B happens to be 5 by 6 into I. You can easily find out what this factor is. Calculator. And you need the magnitude, so the sign is irrelevant. 5000 by 66. 75.75. 5.8 up to 1 decimal, 75. 5.7. Model for BGT, but it's an electrical circuit question. Circuit question. Oh, this is a question that I would do. But here, hey, any questions here? That's it. We are almost done. Okay. We are done actually. But hey, how does this? Should I remember this model for BJT so that I can say answer a question like this? Suggestion is there is either a question from MOSFET or a BJT. Skip it and save the time during preparation. You can put that time in some other subject, reinforcing some other subject. During exam, you can save the time solving some other question. Okay. So NMOS DT cert. Years, 4 years, 3 questions. I would consider skipping that. Okay. In fact, there's a only bit that I would really skip. Most of the other questions is trouble. Okay, so that brings us to the end of this discussion. So as I started, I feel satisfied. I am very, very happy. Hey, microprocessor memory side is miscellaneous, man. I do have that question. I'm going to skip it. Okay. It's miscellaneous. Skip it. Okay. So that brings us to end of analog and digital electronics. Not just that. The end of CARE Biomedical Revision Series. Okay. So even any student right now, the moment this video is out, okay, I'll also put controls S and S before I put this. The moment this video is out, which will be before GATE 2025 exam, thanks to YouTube, okay, any student has access to DM preparation material using which they can get a single digit all India rank and get you this far. Okay, so no, notice this is recorded, so I don't have to spend time on this again. This is I'm addressing any student. So I am quite happy. I'm quite satisfied. Because I'm more satisfied, physically satisfied, because this is publicly available for any student. So this accessibility issue, approachability issue kind of sorted out. And I also, this is a complete series, right? I am not like this subject, complete series, 4 years of PAQs. The ball is in your court, okay? So right now it's up to the students. If you need me to spend any more time, of course, that's going to cost you. Okay. You'll have to join the class. Will it always cost? There are going to be scholarship tests and all that. Okay. So whatever it takes for me to make this sustainable and my time and effort, worth it or valuable. Okay. I'm going to charge it. But right now, not just a steady guide, but also a steady material available to you. Okay.